All right. As everybody comes in, thank you for, I think we've got folks muted as you're coming on in, but we'll keep an eye on that. Welcome to the July meeting of the Salt Lake City R user group. We are glad you're here. I'll just share a few things as we're getting settled and get started here. I'm sure you probably found us through our meetup page, but I will drop that here just so you can make sure you have that. And that's where we'll post upcoming meetings. I think we're going to have one in towards the end of August, I think. And then we've got another one scheduled for beginning of October. So we'll get some various meetings set up in there. Maybe September we can do an in-person networking gathering. Maybe that would be a good time to do that. So we can find that here at the Salt Lake City, our user group. Our goal is for this to be a friendly and professional space. So we use the R Consortium's Code of Conduct. We can look through what that is there. So Andrew and I are the organizers, and so we're the ones that will be moderating the chat, and we are really happy to build a space that just as if we were in person, that we treat each other with respect and professionalism. So we're very glad to be able to have you all there. I'll drop this probably at the end of our meeting as well, but just so you know, the USAR is happening in just a couple weeks, and USAR has a virtual day that is free. So I'm going to drop that here in the chat. So the free virtual day for USAR is August 1st. Is that right? It is, yes, Friday, August 1st. And so there's a slate of talks that are going to happen that day. And since it's all virtually, like everyone's here who is here can register, and I dropped that link there. You can register, and then you'll get the invitation and can hear USAR's the virtual talks for USAR happening this summer. There's also in-person USAR, which is happening a little bit after that as well, but the virtual day is available to everybody. So those are our main announcements, I think, that we have. We are really glad today to be talking about sparsity and tidymodels. So really excited to have Emil with us. So Emil Wiedfeldt is a software engineer at Posit who works on the tidymodels team and improving R's modeling capability. So Emil maintains several packages that are about modeling, about text analysis, about color palettes. And one other thing I always love about Emil is that Emil takes his slides seriously, and his ability to make slides really it is always very motivating, I think, for seeing your slides for me, Emil, because they are always so great. So I'm excited to see what we have here. So the Emil and I have written a book together, which I can drop the link for, about supervised machine learning for text analysis in R. And also you're working on a feature engineering book as well, Emil. So we are so glad to have you. Hopefully I didn't overhype your slides too much. And thank you so much for preparing. And we are really happy to have you to talk about something I have also cared about for a long time. And it's really exciting to see coming to fruition, which is about using sparse data structures and tidymodels.
Well, thank you so much for that introduction. Speaking of slides, I put a link in the chat so they're all live now, so you can follow along. Yeah, I've been thinking about this for like longer than I've been at Posit. Like this started a couple of years before I joined Posit, and it's been just a long like time coming, and we finally got the work done. Yeah, so it's and uh, feel free to ask any questions as we go along, and I will try to answer if then it won't be answered later down the line. All right, so I think this is all best explored with a motivated example. So here we have the flights data set from the NYC Flight 13 package. So it's a um, data set where each row is a flight that happened from like I want to say from the New York airport to somewhere else. And there's a bunch of different variables with it, what plane it was, how delayed it was, and when it took off. All these different types of informations. And in this example, we want to predict how delayed the arrival was as a numeric. So it's a numerical value that can either be like positive or negative depending on if it's delayed or it arrived early. And to make the modeling problem a little bit more realistic, we are removing the variables, uh, the arrival time. So we're pretending that we're predicting when it leaves, if it will arrive on time or not. And for that to happen, we also need to exclude the variable how long it took and when it arrived. And likewise, there's also this time hour variable that is a duplicate variable. So that's a date time variable, but they have all the dates and times already encoded as some numerics in there. And we're doing these standard things where like we're imputing the mean or numerics, and we're handling missing values in all our factor variables, and then creating dummies of everything. And then using XGBoost boosted tree, putting it all to a workflow. So the question now is, what happens when we try to fit this model? And a couple of like notes in it, we're using XGBoost, which is a fairly performant model type, but there's a little wrinkle in this that two of the variables have really high cardinality of the factors. So it's like tail number. So then what plane, specifically what plane it is on it, and their destination. And there's a lot of different destinations. So we end up with over 4,000 variables just from the creation of the dummies. And it also runs on a single core. And I want to say the dataset has about 300,000 observations. So it ends up being quite a big dataset. So what happens? So if you fit this model a year ago from today, it would take like a little bit shy of 500 seconds. So this is around 8 minutes, which is quite a long time, but it's also quite a big data set, right? It's 300,000 rows, 4,000 columns. It's quite beefy. But if you ran it today, it would only take 4 seconds. And it's the exact same model that's being run. You get the same results now than you did last year. So what have happened, and this is really what the talk is about, that we allowed this drastic of a shift to do. And I'm going to tease a little bit now why it happened. Because last year, it needed to allocate 82 gigabytes of data on my machine for this model to be able to be fed. And today it's only 800 megabytes. So I would argue that these numbers are very related to each other. All right, so then what happens? And we'll go over everything that happened. Like I'll try to do a little timeline explaining from the ground up what makes all of this happen. And to do this, we need to talk about what alt-rep is, then how we can use it with something that's called sparsity, how it's integrated into tidymodels, and then lastly, how it affects users such as yourself. So we'll start off explaining semi-quickly what alt-rep is. So it's short for alternative representation. So it's a very R-specific thing that they made, and it is allowing some interesting calculations to happen. And this is a list from the official documentation that some intended uses would be. But the way I like to think of it is when you run a function on some input in R, normally the 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 thing is found in memory. So if it's on a vector, you find the memory area, then you pass it to a function that knows how to work with that. for calculations. If it's a mean, it will just go over, count how many there are, sum them all up, and pass them back to you. But in alt-rep, ads is found in memory, but it also has some type of metadata associated with it. And then when it's passed to this function, it will learn for some functions, does this have metadata? And if it does, we can use it to help our calculations. So this could either almost bypass the calculations or do other things entirely. And I think this easily shown with a couple of examples. So the first example is this idea of a metadata. It's technically a wrapper method, what they call it, but the idea is the same. So if you take, I create this vector called vet1, and it's like 10 million like random number, all these numbers between 1 and 10 million, and then shuffled. And when we sort this vector, it takes 200 milliseconds to sort it the first time. And then we save that to vet2. But now if we try to sort the second already sorted vector, it run basically instantaneously. The reason why it run instantaneously is because the output of sort adds this wrapper with metadata around it saying this vector is sorted. So when it's then being passed into sort, it notices, oh, I'm already sorted, just return me straight back out. So this is one way alt-rep is working. It has this like notion of sorted, like it adds sortedness to something. If we then instead took this sorted vector, that vet2, and add a 0 before it, we know it's still sorted because the numbers are 1 through 10 million. We add a 0 before it, it's still going to be sorted. But it now lost this metadata around it because it's very fragile, and it now takes, it's faster because the method doesn't have to do anything to shuffle things around, but it doesn't know it's sorted anymore. So we lose this idea. So this is one of the way alt-rep is working, has this metadata, knows when things are sorted. Another example that's a little bit more complicated is the idea of integer sequences. So these are sequences you see when you do like using the colon, so like n colon m. I use a lot of like 1 to 10 or something like that. Or you use the sequence function or the other sequence friends, like sequence length and sequence along. And they'll look like this, like they have a bunch of numbers from something to something else. And here I could fit 18 on the screen. No, 28 on the screen, but sometimes it's in the thousands or millions, right? It's a lot of values. And if we then look at it to see like how does the size in memory, how much memory does these vectors take up? So on the left-hand side, I'm creating numeric vectors. And this probably should have been integers, but they're numeric vectors. And so numeric of 100 creates a numeric vector that's just 0, but 100 times, next one 1,000 times, and next one 10,000 times. And we see, as we would expect, that the size of the object is linear to the length of the object. But when we, on the other hand, create these sequences from 1 to 100 or 1 to 1,000 or 1 to 10,000, it's always the same size in memory. And then because we're using all this is also a place where they're using alt-rep. So what's happening is I'm using this package of from GitHub that has some alt-rep accessor function, so you can look at what happens a little bit underneath. And what is happening is when you create a sequence in R, it will create an alt-rep vector that has some metadata in it, and the metadata is 3 values. And it's always done for 3 values. And the values are how long is this sequence, what value does it start and how much does it jump. So when you create a sequence from zero, like from 7 to 100, it has like 7, like 100 minus 7 plus 1 value, so it's like 74. It starts at 7 and it increments by 1. And like I was going to do for 1 to 100, 7 to 100,000, we see a larger length, but the same start and the same step or increment value. So this means that any sequence will take the same amount of memory in space. So it means that whenever you try to use an alt wrap, some things happen, it being like detected underneath the hood. So when you talk like length on a sequence like this, instead of looking up how much memory it takes up somewhere, it just pulls out the first value of this metadata down in the internals. Likewise, if you want the sum of this sequence, it's like quite I want to say like it's just a simple algebraic calculation. So it just pulls all the values and multiplies it in the right way, and you get the sum. So it doesn't have to go over all the values. We can just do the math like this. And so that is like, in essence, what happens in alt-wrap is it defines some metadata. Sometimes it's added on, like when we saw in the sorting example. Other times, here in the sequences, the data doesn't even exist. It just has all the sufficient information that's needed to do things with this sequence. For alt-wrap, or no, for these integer sequences, they work really well for alt-wrap because while they can do a lot of interesting things, they're also very fragile. So here's a list of all the methods that you would need for integer. So that's just general alt-wrap stuff. So if you need to like get the length or like make a duplicate or like turn into something else, they have methods for that. You need to write up. There's also just some general like vectors information. So sometimes you need a pointer to the data and other things. And then we have like specific to integers. So like give me a region, or is this function sorted? Or does it have a sum? Or well, what's the sum? So like is sorted very easy in the sequences example because it just needs to check is the increment positive or not. So it doesn't have to even look, just looks at one value. So that's fast. But if you try to do anything that's not on this list, it will be forced to materialize. So essentially create a normal vector, and then that normal vector will be turned into it. So these integer sequences are perfectly suited for alt-wrap because you rarely modify an integer sequence. It's typically created for in a for loop or other places, but it's very rarely you create it and then want to update the second value to something else. That doesn't really happen that much. So having that alt-wrap primer of what we can do with it, we now move on to the idea of sparsity. So sparsity is this like statistical term that essentially means that something contains a lot of zeros. So it isn't a 1 and 0 situation. It's just how many of these values are 0 in this data set. And then the opposite is what we call dense. So when it doesn't contain a lot of zeros. And there isn't always a threshold point. Um, so it's not like when you have more than 80% it's considered sparse and less than 80% is not sparse. Like it is, there's a very like it's a feel on it. And a lot of times it doesn't really matter that much because when you have sparse data and you feel you have sparse data, it's like 99.9% zeros. Like it's a lot of times very obvious when you see it.
We have a
Yeah.
question actually, Emil, just about this. Like, what does it mean for something to be sparse? And someone was asking about the idea of zeros being there versus missing data being there. Do you want to speak a little bit to like, what do we mean by zero here? And what is the overlap with like highly missing data or the differences between like
Yes.
really missing data?
So it's a good question. It's a little bit related to implementation. I think it's mostly implementation detail. So in the R package matrix, the the sparsity is related to the number of zeros. But I know some Python implementations consider sparsity as the amount of missing values. So like you could consider something where like most of them are missing to be sparse as well. So it really comes down to like implementation, and especially if you have both. Because what if you have a lot of zeros and some missing values? I would treat the missing values as different than zeros. So, but it is like some people have a high sparsity in a missingness. For this thought and in my word, I have treated sparsity as related to just amount of zeros. But it's a valid question.
It is interesting too, like when I think about the language example, it's like what does a zero mean
Hmm.
versus what does a missing mean? You know, like they mean probably different things.
Yes, so I think it's very specific to your domain. So like in the natural language processing, a lot of at least the part of natural language processing that I enjoy is very count based. So it's how often in this document does this thing occur? And if you end up counting a lot of things, then there will be a lot of zeros plus, oh, this pattern this did not occur in this document. And this other pattern also did not occur. So if you end up counting a lot of things, you end up getting a lot of zeros, but it did not occur, right? So it could be an encoding thing too. What is missing is also a very interesting question. But it shows up a lot. Recommended recommended systems. Like if you're on Amazon and if you like, I haven't bought. I have used it a lot, but I also haven't bought anywhere near like 0.001% of all the items on Amazon. So if you created a user, a customer by item matrix, that is going to be insanely sparse because most users haven't bought most items. And you also get sparse data just as an output of feature engineering. So interactions, especially from already sparse things, produce like explodes the sparsity, and dummy variables and other like count-based things end up becoming quite sparse. So it's worth like looking into. It's a field that a lot of people like something that people see. So here we have a sparse vector that has some values, but they're mostly zero, and I put a 4, 2, and a 1 in there. So the question is, as with our integer sequences, is there a way to rewrite this vector using fewer values that still stores this information completely? And we can do it with with these like three types of values. We have the length, which always going to be one value, it's just integer. How long is this vector supposed to be? Then the positions of the non-zero values and what values those take. So here, that is variable depending on how non-zero it is. So for this example, we could condense 36 values down to 7. So which is like quite an improvement. But you also notice here that it takes like we spent twice as much data finding these non-zeros. So if it's half 0 and half not 0, it's technically less efficient to store it sparsely than to store it like normally. So there's a threshold, and then most sparse operations are less efficient computationally than the dense version. So there's some threshold of when is it useful to keep something sparse or not. But a lot of times when you have it, it's at 99% sparse, so it stops being an issue. And we can see a little bit here, teasing a little bit later. So here I'm creating a sparse integer with some values and a length. And on the left-hand side, I'm increasing the length, making it 100 times longer, but it doesn't change the amount of memory it takes up in space. On the right-hand side, I'm going from 1 value to 5 values, and that is increasing what it takes up. So now we don't have to worry about the number of observations anymore. It's only the number of non-zeros. So we are effectively, it's a type of data compression, but it's data compression that is analytically favorable. Like if you gzipped something, it's not as useful because we can't easily pull out information we want. Here, we can still pull out things that we want for later use. And for the sparse operations, we can then use this metadata to then give you bad information. So like if you want to do the sum of a sparse vector, we just sum over the values it takes. So this would allow something to be very fast, but there will be less, so it'd be faster than doing it in a dense way. The mean we do the same way, we sum over the values, divide by the length, which is already like defined in it, so we don't have to calculate that. And other things we can do too. So I think I wrote it correctly, but if you wanted to pull out one element of a sparse vector, we then see, is this index part of the positions? And if it is, we just match it to the corresponding value vector, or if not, we just pretend 0. So we can do a lot of the same transformations as with a dense vector, but we can still produce everything we needed. Here's like the main downside of this is that alt rep only works in C, so it's all like connected to C level. So here I copied over this integer element. So if you have a sparse integer and you want one element out, so you want like a 10th element out, this is the code I wrote to do that. So it becomes a lot more verbose, but you need to handle everything. If you notice, it's a sparse integer, so it has a different function, slightly different code that handles the double variable, so it enumerates. And there's a lot more edge cases. So what all this led to is I wrote this package called sparse vectors, and that one does everything that we really needed. So everything happens in C. So all the alt rep creations, so creating the vectors, modifying them, materializing it, all of that is in C with a couple of helpers in R that we needed as well. The hardest thing about this is it needs to match everything we do with the normal one. So if you have a sparse vector and you add 1 to it, it still needs to do the same thing as if you did it on a dense one, or if you subset it. Still it's the same thing, which includes what happens when you have missing values or infinites or not a number. Like all of that has to match 1 to 1. We can't not match it because that's like part of the deal. So there's a lot of like writing the first part is easy, but making sure it also handles infinites and not a numbers and missing values and combinations of those, it all has to work out. And that ends up being a lot. And you need to write everything for each data class. So it has sparse integers and sparse doubles. They have to be handled separately. There's a lot of minutiae in that. It's very fragile, as I said before. So if you try to do something with an alt vector, it doesn't know how to do it. It needs to materialize and create the dense version. So I wrote there's a materialize function in sparse vector. So if you try something in a sparse vector that doesn't work, it will just create a dense vector and then return that, which is slower. And also, we're doing this for a memory perspective, so we want to avoid as much as possible to materialize, because that is where we're really gaining all the benefits. And I created a total of more helpers. So I think its variance is not an alt rep thing, so we have the mean, but variance is not. So I wrote a sparse variance that will calculate the variance of a sparse matrix, of a sparse vector, without ruining its alt repness. It also contains some converters between sparse matrix from the matrix package and our sparse tuples, which is a tuple with sparse matrices, sparse vectors in it, which you can seamlessly go back and forth between them. And for the most part, the users don't need to know about this package. So this is just a central place to put it. But this is mostly made for us to allow things to happen, because alt rep for most parts will be invisible to the user. So this is mostly what happens internally, but it could be used if you have a use case we don't have supported. So for the integration part, we need a couple of things. So the first thing is, why are we doing this? And I know this is late in the talk, that why are we doing a bunch of things? But the main hurdle was we wanted to handle missing data, no, sparse data in modeling, because it comes up a lot. And when it comes up, it really matters. If you remember the example at the beginning, uh, a model took 100 times longer to run because the sparsity of the data was so extreme. So for some people, if you don't support sparse data, it either takes too long or doesn't run at all. Because then something that could take up a petabyte of data in memory could take up a terabyte of data in memory if it was dense. So like it can really, you can use data sets that you couldn't use before because the dense representation wouldn't fit in memory. And now it just works fairly easy. So sparse matrices doesn't work with tuples, and tidymodels is built with tuples. Like tuples is like the first order citizen inside tidymodels, and we would have to basically write another tidymodels that supported sparse matrices if we wanted. And sparse matrices have this, while they are awesome and do a lot of things, they are first and foremost matrices. And one of the constraints in a matrix is that all the columns have to be the same type. So if we had a fully matrix, like sparse matrix ecosystem, you would never be able to do classification because you couldn't put a factor into the matrix. It has to be numbers. So now we have this notion of a sparse tuple, which is a tuple where we put a bunch of sparse vectors inside of it, which allows us to have sparse data and non-sparse data in the same data structure, allowing us to only work on what we need to. And then we have these helper functions that lets us move back and forth between the sparse matrices and not. So we can have some data that's dense from the beginning, recreate some sparse data, put in it alongside its non-sparse versions. And right before it goes in to the model, at the XGBoost engine, we can turn it into sparse data in the right way, so we get all the speeds without any of the slowdowns. So what was needed for this came like in three major parts. So the first thing is we're moving tuples around from function to function inside of tidymodels. But we needed to verify that none of them did things that would break the sparsity. Because if you load at an alt rep vector wrong, it wants to materialize. We want to avoid that. We can also produce sparsity. So I mentioned like step dummy in the beginning. That creates real high sparsity, especially with if there's high cardinality in the factors. Then it becomes really sparse. So we made it so some of the recipes that produce sparse vectors instead. And then lastly, to make the user experience as smooth as possible, we have this automatic toggle that turns on and off the sparsity production to make life as easy as possible. We'll go over them one by one. So the internals, we need to make it so the sparse matrices. So one of the benefits is now we have sparse matrices support as an input in everything. So if you pass in a sparse matrix in like a recipe, a prep, a fit, predict, the first thing that happens is there's a chat saying, are you a sparse matrix? If you are, we turn you into a sparse tibble. And then that just floats through all the way across. So most of this work is really just a lot of chatting, making sure we didn't break anything. And but one thing that could happen is if you told as matrix on the data, then back to as tibble. Something like that, or like something in between it to do something fast that would just happen to be faster as a matrix. It would break the sparsity and have to materialize the whole thing out and we lose it. So a lot of chatting and avoiding some functions that didn't do sparsity the right way, or creating helper functions to do it in a non-breaking way. So now it flows right. There's a couple of times. So if you use a formula in a workflow, you can't use sparse data because it goes through model matrix, model frame infrastructure, and that turns our data frame into a matrix internally. So that doesn't work. But all other cases, I was able to route the data around inside tidymodels in such a way that the sparsity is preserved from end to end, which includes at the very end, when it gets to the parsnip model, it will turn it into the format that it needs. So if the model supports sparse matrix and we can do it and it's sensible, we turn into a sparse matrix in the right way and it's passed in. And otherwise not. In recipe steps, there's a couple of some of the steps produce sparse data. So the common one is step dummy, but also like total frequency steps. So a lot of test recipes also has the opportunity to produce sparse data. And the ones that can produce sparse data have a sparse argument added. And it can take three values. So it can take yes, no, and auto. So auto is the default, and it will let tidymodels decide what to do, what it needs to convert. But you can also override it. So if you know, yes, I think this should produce sparse vectors, you can specify it to yes. Or if you know, hey, I'm doing these things, but I'm going to use them in something that will break sparsity or won't support it, you can just set it to no, and we won't go into the trouble. Because if you do something that won't benefit from it being sparse, you shouldn't do it. Because it's slower to generate the sparse representation and then having it materialize back to dense than just creating it densely to begin with. And this is why the automatic toggle comes in. So we wanted to make sure that this happened when it was useful, but didn't happen, like made it as good as possible for as many people as possible. So there's really two questions. So does the model support sparse data? And is there high sparsity in the data? So this comes with like a couple of things. So like XGBoost supports sparse data. Um, LibLinear supports sparse data. Like GBM supports sparse data. So there's a couple of engines that support sparse data and have been set up for it. And then there's some that just don't. Like some will just call an S matrix on it, so we don't want to do it. But then the second question is, sparse data only helps as the representation if the data is actually sparse. So the number one is already done. It's part of the encoding. When you add an engine, you specify whether it will want sparse data or not. The second one is harder. So the way we do it is, it matters a lot for the parsnip model. So it has to be an estimate of how sparse data is after the recipe is finished. But we want to know this information before the recipe is prepped, because we need to throttle whether the recipe needs to produce sparse data or not. So the way it's done right now is each step that produces sparsity have this little method that will give an estimate of how sparse the data will be. And like for step dummy, it looks at what columns we are adding step dummy to, looking at the factor levels of those variables, and then trying to do the math backwards. So we remove them, and these newly created variables have this roughly sparsity, and like give it an estimate of it. And it's not perfect because it doesn't have like the ordering, but it works fairly well. And we can estimate roughly what the sparsity will be. So then we ran a model, ran a simulation study where we took a bunch of different sizes of data, so number of rows, number of columns, different amount of sparsity, so different amounts of sparse variables and non-sparse variables. And we fit them with a combination of all the supported different models. And that takes like 100 hours on my machine. So it runs single core, not being touched, and that creates a bunch of data points. And we have the same model being fit in a sparse way and a dense way. So then we take a lot of the difference of it and use that as an outcome. So we're trying to have a model that predicts whether whether the dense model is faster or the sparse model is faster, uh, purely as a thing of time. And for this, we used a mass model that seemed to work really well. And I used orbital, which is like an extension of tidypredict, that turns this fitted model into basically R code. So we are embedding this fitted model into workflows. So workflows, you give it a workflow and it looks to see if the model supports it. If the model supports it, it looks at how big the data is, what sparsity does it have, number of rows, number of columns, and then it will plot it into this mass model, and it will do a prediction on whether this model will benefit from being sparse representation or not, and then toggle this auto arguments in recipes to either yes or no. So this means that there's non-native support in sparse data as an input, and this automatic toggle will mean that most people probably won't have to do anything, but it just does it. We try to set the threshold so for most people it shouldn't matter. Like we set it so it might not always benefit you, but hopefully it doesn't make anything slower. And if it does, you can set the sparse argument specifically in the steps to turn it off. So basically, if you've set sparse equals to no in the recipe step for sparsity in it, you get the behavior that you had all along. So it's a non-breaking change in that way. Uh, yeah, and that's it. So it's a sad affair in the sense that for most people, they don't have to do anything and it just works. And sometimes it's really fast. And so hence the low toad um, slides.
Awesome, Emil. Thank you so much for walking through that. That was really interesting to hear. As someone who myself has also been really interested in this for a while, I love, I would, I don't know, there are a couple of things I'd love to hear more about. But if you have a question and you're here, you can type something in, or if you want to use the hand raising feature, you can. Or I think I do have the Q&A feature open if you want to prefer to use that, whatever you all have questions about. I want to start out by asking you about the simulation study. Did you all, when you were working on that, can you say a little bit about like some of the choices you made going into the simulation study? Like, what was it that you were trying to understand where cutoffs should be? Or I love using simulations as ways to make decisions. I think it's such a it's like I don't know, one of the reasons I love it is because I feel like it helps you and like the person people you're working with or with yourself like get really concrete about what is it that matters to us. Like you get your assumptions kind of out of like what you're just talking about into code. You're like, okay, here are our assumptions. If we can both look at it, we can agree on what we think we're doing. Anyway, can you say a little bit about more about that? I was super interested to hear about that.
Oh, thank you. So yeah, so it's linked in the slides somewhere, like
Okay.
in the footer, so you can find it.
Okay, okay.
Um, and everything like, everything we do is all public. So, but what it has is, so we have a number of, it's mostly number of rows and number of columns, and then different amounts of sparse data and non-sparse data, which then that gives the amount of sparsity, right? And there's some, no, I just ran it. So there's an interesting thing right here. So I just had it right here. So this is one of the plots from the.
Ah, interesting. Okay, okay.
So what's interesting here is so at x-axis, so they're both the log fold. So they're both uh, higher values above 0 means that it took longer for the dense, and values for the below 0 means that the sparse was faster. And this is like our predictions, there's the non-predicting. But what I find interesting here, well, first of all, Ranger says they produce like handle sparse data, but they
Yeah.
don't. So they just
Hmm.
call as matrix
Like
in
right
sparse
away. Like
right
right
away, or
away.
like
Yeah.
hidden somewhere. Like they don't handle sparse data at all. They allow
Yeah.
it as an input. They don't do
Yeah.
anything. But then you see, especially noting the GlemNet and the light GBM. Um, Glennet really like care about the sparsity.
Yeah.
Because
Yeah.
the slope is so steep that
Yeah.
it really matters. Well, light GPM honestly like doesn't really matter that much. Like it can handle it and sometimes it's better. And also these are large things. So like in the Glemnet one, the biggest one is like almost like 500 times slower. So that's like a lot, right? So that is that's one of the things we noticed is. And likewise, in the lib linear one, most of the predictions are like below 0, and XGBoost, most of them are like above 0. So there is, on a model by model side, how much they benefit. We realized very quickly that we can't just have a global thing saying 80% sparsity.
Yeah. Right. Yeah.
Because that's not true at all. It really matters on the model. So that hence we needed the thing because some of them almost always want it sparsely. Like even with like 50%, they're like, we love it. There was more
Yeah.
sparsity. And other ones, you really need a really high degree of sparsity before the computational side hits in. And
Yeah.
this chart is strictly time. This is how long it took to fit, right? So so that is really what lifted is, and even if it was the same thing, we wanted like just the numbers on it. And it also matters. So like for some of them, it triggers when with more rows. So like the same amount of sparsity, like 90%. It might be faster densely if you have a thousand rows, but 10,000 rows, it becomes faster with sparsity. So it's like, is it perfect? No, right? Like there's definitely more to it, but I think it has a decent like threshold with everything in there. The thing is, it also takes a while to run,
Yeah. 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 Yeah.
and it's run and we run everything multiple times with any combination. So like we do a resample of it.
Yeah. Right. Right. Yeah.
So it's yeah, it's and yeah, and also because this is essentially just a if else statement. So I'll find it. I can show it fairly easy. So this is it's a little messy, but all of that just led to this code right here.
Hmm.
So it's just like there's an intercept where it takes different values of sparsity and number of rows or not. So a lot of this is like so this one is yeah, so a bunch of different things in here, and then so they all share an intercept somehow in this model. And then if it's XGBoost, we add on some values depending on something. If it's light GBM, we add some other values on it for other things. It's if it's Ranger, we just say no right away.
Yeah. Right.
We know it doesn't matter, so don't
Right.
try. And it all looks like it's big because that's just what it is, right? But it's
Yeah.
like
Yeah.
that, and that was really came out of the need of we don't want people to have to specify it for everything.
Yeah. Yeah.
Like,
Yeah.
that
Yeah.
seems like too much, and no one have complained,
Yeah. Yeah.
and it affects everyone. Or if you run XGBoost, it most likely did something.
Yeah.
You just didn't see it, or like just thought, oh, it's faster now.
Yeah. No, that's really interesting. And I guess as we come up against the end of time, if anybody has a question they would like to type in, go ahead. But I guess if not, I'll ask one more question. I kind of, as you think back on this process, what part of it do you feel like was the part that, as you were working on it, provided like the biggest challenge? Like you thought about, okay, I had to do some of this work with at the sea level. I had to do like figuring out what of we support do we need to figure out to we make a change. As you think back, maybe if you can um, think back about what got you to here, which was the part that you found the most challenging?
Yes. To answer the question in chat first, this is live as of like of March, something like that. So this is what happened now. Like it's just in it.
Yeah,
There's a tidyverse.org blog post about it that also explains it. So it works if you install it after that. But it also is done in a way so if you don't have all the pieces, it just doesn't hit in. So it tries to be very like conservative when it hit in.
yeah,
So there's a couple of points in this journey. So I've been wanting this for like 6 years.
yeah, yeah,
So one of the things is like the political will to do it. It took a while to explain to the right people that this was useful in a way to like get it off the ground. And I was able to do it eventually. That let me like work on because this was a big thing of what I did in the last year. Like this was a huge undertaking across basically all the packages in the ecosystem. Um, this C is hard because it's C,
Yeah.
And because alt rep is not documented that much.
Yeah. Yeah.
Like I spend a lot of time um reading either like the R source code or going on the GitHub mirror of all the train packages to see what other people did with alt rep. But it isn't used that much. So like that part is hard, but like Davis Van helped me with the C code and he's like great at all that. So like I appreciate like everything he helped with. So I think technically I think writing C isn't that bad. It's finding like it's the weird little things of why am I doing this? And it's like a type it's not even a typo, it's like, oh, this is just convention that our taught doesn't write or I couldn't find.
Yeah. Yeah, no, that's really that makes sense that that would be a challenging one.
And it's a thing where it touches everything. So like
Yeah.
it's really hard to start testing it because it just is all of tidy models that like really touch on it. So finding the right examples to write a test on it. Also, this is invisible.
Yeah.
So I technically have a global option that you can turn on that would then omit errors or warnings from the materialize C function as a way to test that it didn't materialize. Because a test where you could feel it would be too slow to run on train.
Yeah, 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 yeah. For sure. For sure. Yeah. Nice. Nice. Well, Emil, thank you once again for coming, for sharing about what this journey was like as you went through it, giving us so many details about interesting things that are happening. And thank you all so much for coming. We're always really glad to see folks both from the Salt Lake City area and from around many other places as well to join us. I'll drop here at the end, just since it's coming up pretty quickly again, the info about the virtual program at USAR. So it is happening on August 1st. So you can sign up if you want to hear some more, learn some more stuff from various R people during that USAR day. So we will see you in the next month or two, and you can keep up with us on our meetup site. And I want to say again, thank you so much to Emil. I think we're all really glad to get to